Okay, so now that Adam has completely removed any concerns about cloud and we're getting perfect clear sky imagery, we're going to talk about where the problems don't stop. So sadly, even after you've removed all your cloud and you're absolutely certain you're seeing straight through to the surface without aerosols or cloud, well, maybe not some aerosols, there are still issues that you then have to deal with in any form of TIR retrieval. So I'm going to go through a few things. Firstly, why we care, and then how it affects retrievals, how we know it affects retrievals, sort of into why, and then what we could do to start accounting for this, while being very careful to talk in a general and nondescript manner so I don't talk about any retrieval algorithm in specifics, because Agnieszka will cover that later. So the first part is actually quite easy to address. Why do we care? It's because we get things wrong when we don't. Fundamentally, the thermal temperature that we're trying to retrieve, whether it's the sea or whether it's the land, we are looking to see through the atmosphere. And if we fail to account for it, we're going to get things wrong. So there's a lovely number highlighted in red here, which is 12 Kelvin. This is a study that was looking, if you had very poor estimates of the atmosphere that you were looking at and didn't really take any serious effort to account for it, you can have errors. And these are real errors, they're not uncertainties on this, is in the simulated domain. We can go up to 12 Kelvin. Now, there are very few applications that can survive that sort of uncertainty or error on them. Basically, none that you're going to be doing with any retrieval algorithm. So you've got to account for it, otherwise you are in a lot of trouble. Now, a huge amount of this is water vapor. I'm not talking about the water vapor that we're doing in cloud detection. I'm talking about the stuff that's going to be there everywhere, hopefully, otherwise humans are in a lot of trouble if water vapor disappears globally. So you do still have some aerosol contributions and you've got other gases, and I will go through a few of those key ones later, particularly where they pertain to common channels that we look at in the thermal infrared. A bit of a disclaimer on this as well, though, is I'm going to come at this from a satellite perspective. And the satellite perspective is where most of my plots and most of the theory I'm talking about. But if you're in aerial or drone, do not think that this does not matter. It absolutely does. Just because you are lower and closer to the ground, and you may think I've got less atmosphere in the way. We recently did a campaign where we were looking in Italy over some agricultural areas, and they had this high-resolution, multispectral thermal imagery being taken over it. And the initial results came back and we said, well, this doesn't look right, because we had validation on the ground as well. And we were looking, as you can see from the distribution on that histogram there, an average of 3 Kelvin difference up to 6 Kelvin difference. So we're talking an aircraft. Usually there's a lot less going on here. We've got an idea of how the validation, the resolution is closer to the validation that we're looking at there. It should have been doing really well. And essentially, this came back to the fact that in their retrieval algorithm, they hadn't plugged in the altitude of the sensor correctly. So all of this coming through, even that little bit of atmosphere between the plane and the ground, you did that incorrectly. We're talking 3 and in some cases up to 6 Kelvin error, even on this. So while I'm going to be talking very strongly from a satellite perspective, if you're interested in basically any remote sensing, so there is some atmosphere between you and your target, this still applies. So very much to build on what John showed you earlier, going back to a bit of basics, why are we seeing these effects at all? What's going on here? So this plot is a bit of a simpler one to show you how we go in the different regimes, and specifically when we go towards the thermal, what we're looking at here. So transmittance, as we've said, is how much of the radiation we're actually managing to get through the atmosphere without getting attenuation. But as you can see here, this shape is irregular. And as John showed before, there's a spectra to it. We're not seeing all of it going on there. So we've got a percentage loss as well as things that are being emitted as we go along. And in the thermal, you can see there's these bands here, these window regions where we're getting a bit better transmission than we otherwise would. But what is actually causing this? It's not a ubiquitous number that an atmosphere just doesn't possess a transmission and that's it for this place on Earth. So, as we've seen before, there are different gas species in the atmosphere, and each one of those gases absorbs, transmits light that goes through it in different ways. And they do it across different parts of the spectrum. So this goes from 7.5 to 8 in the top plot, then from 10 to 10 in the second plot, and then from 10 to 12. So you can see that it's not even that there are one or two species that we say, oh, this is the affecting gas of the thermal. Even as you move through the thermal infrared that we commonly use for most retrievals, different gases come into play at different times and can have radically different impacts here. So what does this look like in practice? What we've done here is these are theoretical species from like lab results, so I can clearly see each of the lines. Well, this is a more practical example. So these are two gas atmospheres that have plugged through a broad model. These from the MEPAS standard libraries. This is a mid-latitude summer atmosphere and a tropical atmosphere. So the tropical is in orange and the mid-latitude is in the blue. And you can see while most of the lines have a lot of similarity here, we're seeing many of the same features, there is a dramatic drop in the transmission when you go into the tropical atmospheres. A huge amount of this is due to the water vapor. We have increased amounts of water vapor, even in our beautiful clear sky settings where we pretend clouds don't exist. But it's not completely for that. There's other species going on here. But also you'll notice it's not just as simple as, oh, well, you drop it by a certain amount. You can see even on this scale, where you are in the thermal infrared spectra makes a huge difference to what's going on here. If you look towards the 8 to 8.8 micron here, where there's a gap, and you can see it's a sizable gap, you move towards the 11, 12 here, you can see the scale of the difference between the tropical and the mid-latitude atmosphere varies quite a lot. So we're now moving into the idea that we've got these different sensors, and even the channels on the sensors, of which we usually have at least two, not in Landsat cases, it really matters where they are in terms of which of the gas species are actually going to affect them. So here we're going to move into looking at a sensor briefly. So as John said before, we like to focus on multi-channel instruments, gives us a lot of information, particularly when we look at these high resolution ones that we were looking at before. So this is ASTER. So ASTER has 5 spectral bands. It's got 3 bands in the 8 to 9, and it's got 2 bands in the 10 to 12. Now, we group them like that for a very good reason that you can probably see, but I'll go through on this plot in a moment. So what we've got on these plots here is simply the Jacobian. So the Jacobian here that we're talking about is actually the top of atmosphere brightness temperature, which is what we'll commonly be talking about in terms of brightness temperature at the top of the atmosphere, the observation, how much that is affected by the changes at each level of the atmosphere of a parameter. So I've got a nice easy one. We're going to look at here. This is the top plot, is the atmospheric temperature. So it's got the beautiful units of Kelvin per Kelvin, because if you've got Kelvin changes at each level of the atmosphere, how much impact does this have on the top of atmosphere brightness temperature? And we've broken it down by different colours for each of the channels. There are differences between them, but they broadly follow the same distribution, just with a little bit of width when we go to the denser pressures. But I've included one here, which is ozone. And ozone is the reason why you will see very often, you'll see it on all the new sensors, LSTM, SPG, Trishna, as well as you see it on ASTER, why there is a gap, why we split everything into 8 to 9 and then 10 to 12. And it's because there's this ozone absorption feature at 9 to about 10 in there that causes a huge amount of loss of transmittance here in the thermal. And you can see this feature here. So this is brightness temperatures at the top of the atmosphere. If we were to have full spectra, so this is at 0.001 microns, I think, going across. And you can see this huge and sudden drop in the signal getting there, which relates to the ozone. Now, we try to avoid that, but the channels that we select for thermal infrared are not beautiful boxes. They are not, as we call, top hats, where they go up with a steep side, go across perfectly and down again. It's not this little column that we take. So what you can see here is this channel here, the later one that's centered roughly on 9 microns. It spreads out, it's got some slope to its sides, and this is enough that it starts to get some of that ozone feature in the spectra. And you can see that when we look at the Jacobian here, the impact that has, this channel has colossally greater impact from the ozone than any of the others. So you've got to be very mindful of not just where you put your channels, but how well defined they are. Are they broad? Are they nice top hat shape, or do they have a more spread out Gaussian shape? As we look at the atmosphere, this makes quite a big difference. So this would be referred to as the instrument spectral response. So this is still, it has impact for the emissivity, but I'm talking about it in terms of the atmosphere here. So a plot that some people in the room may be familiar with, but this is an experiment that basically looks at what happens if we wiggle the channel around a little bit. So what we've got here is a channel that is originally centered on 8.7 microns. And all we're doing is getting the center of this channel and shifting it a little bit left or a little bit right. So the red line on this plot is where we've shifted it towards the lower wavelengths to the maximum extreme, and the green is where we've gone to higher. And what we've got underneath is a plot of the impact this shift has on the top of atmospheric brightness temperature. And you can see that this is not an insignificant feature here. This is quite a lot of change that we're seeing here. And bear in mind, we're not changing the atmospheric conditions of this. This is simply looking at the same atmosphere, but from a slightly different part of the spectra. Now, this is important in two main ways. Firstly, when you're designing your instrument and you want to know where you're placing your channel. Depending on what features you're trying to see, what noises you're trying to look at here, it may become important that you focus on a very particular part of the thermal infrared spectra in your retrieval. But, and this is the more damaging part, it also matters, is your channel where you think your channel is, and is it the shape you think it is? So as you will learn, if you ever go through the process of designing or calibrating an instrument, you will be told we have a channel at 8.7 microns, and it has a width of a full width half maximum of 0.5 microns. And if you go onto a website, you will frequently be able to download these for all the sensors you want. You can find them for MODIS, SLSTR, and you will typically get this one nice, sometimes a bit wobbly on the top, spectral response function that you can say, well, this is what I'm looking at here. What they don't tend to include in that is it's got a plus or minus on it, like anything does. It's got uncertainty. So this is where we think our channel is centered, and this is the width we think our channel has. There is some uncertainty on this because it's not as easy as you could directly translate, this is my theoretical design for a channel, and it will perfectly go through to a detector. Sadly, it doesn't work like that. It'd be nice if it did. So this is important for where you're designing it. Actually, if we're saying that moving them by these small amounts can have this impact, that means every sensor has these impacts baked in somewhere, where there are these small changes due to the absorption you're getting over the atmosphere and the land, but I'm focusing on the atmosphere here, based on the fact that we don't actually know fully where the channel is. So this affects everything, not just when you're designing the channels. So hopefully this gives you an idea of why we care about a lot of the stuff we do with the atmosphere. So there's two main things that we build off when we're going forward from this. So there's correction, which is to the best of our ability, can we get all of these effects to go away? And then there's the second step, which is no, we can't. So how sensitive are we to it after we've done this? And what's the uncertainty that that puts into our retrievals? If step one was perfect, we could ignore step two, but step one is never perfect. So we have to have step two. So this is an even more simplistic version of something that John showed, but I've added a couple more layers in here. So atmospheric correction, we've got the observation. Essentially what we're saying is we want the surface leaving radiation. We're trying to get all the way back there. Again, assuming the lovely clear sky example here. So we've got a diagram here, we've got the surface, it's emitting, that's great. It goes up through the atmosphere, it loses some of its energy as it goes through the atmosphere. There's water vapor and stuff like this. But that's great, but it goes up through layer one, and layer one, well, there's atmosphere there, which has a temperature, it's got an emissivity, so it emits some of its energy as thermal infrared radiation. Some of it goes up with the ground leaving radiation, some of it goes back down. And this continues up through the layers. But, as with all of this, all the energy that is directed back down as radiation to the surface, well, that interacts with the surface, some of it gets reflected, and also goes up undergoing the same process. So there's a number of things we're having to model here. This is just treating the atmosphere as a ubiquitous whole. which is actually comprised of massive amounts of gases. So we do still do this in our practical response to this, but what we do is we make the layers much more detailed. So you add a lot more layers, and you also add a larger number of factors in terms of what dominates the layer, what gas species are there, what absorption lines you're looking at. Now, you can coefficientize this in a lot of models, but essentially I'm going to start off with the most detailed way that you could look at this. And that would be in like what we might call a line-by-line model. So this would be the first way that we could look at this. For reference of this, I'm going to use a lot of my terminology examples from RFM, which is the reference Ford model from Oxford. There are other, what's the BBC one? The other Ford models are available. This is the one I'm familiar with. So this one has a lot of functions that attempt to, as best as we can, actually model the physics that we understand to be going on there. There's still some coefficientizing going on in there. There has to be. It's impossible to do every photon perfectly. But to the best of their ability, they treat everything as a line-by-line spectra. So we're trying to deal with things at the most detailed, small units, in wave numbers in this case, but spectrally moving in increments, traveling through, trying to treat everything at a very detailed level. It's also very expensive computationally, but it gives you a good result. So here's an example that we can see here of directly copy paste code from what I'm doing here, but you give an idea. You give your spectral range, say this is the area of the atmosphere I'm interested in. You give the absorbing species, so you say water, carbon dioxide, ozone, these are the ones I'm worried about. You give it an atmosphere that contains values for these and a profile. Tangent height here, just about to say this is the observational view angle, because the path length changes, what gases you're looking at changes as you change the angle. You need to account for this in what you're doing. And then you set it off, and it will simulate the path of that light leaving the surface to the top of atmosphere and give you an idea through a whole series of quite complicated functions. But this is the most accurate way of doing it for most applications. It is also extremely slow. So when we're talking about atmospheric correction, the general idea is that people think you're taking satellite data and doing it to satellite data. You can't do this to satellite data if you want to give it to users in any reasonable time frame, because this will take a very long time. You'll have to do this every pixel that you're looking at, simulating it through. It is computationally too expensive. You would not be able to put this, definitely not on an operational. You might be able to reprocess for a specific case study, but you're not going to be rolling a technique like this out for your normal retrievals. So then we go on to a more coefficient-based model. So this one, again, I'm going with what I'm familiar with, RT-TOF. So here, it directly already goes to the spectral window. So you don't do this at the full spectral resolution. You give it your ISRF that we looked at before, and it calculates coefficients. So you send off to the nice people who make these for you, and they go away and they run millions and millions of simulations based on your ISRF, and they come up with a coefficient file. And it's basically a file for each instrument that says, this is how your instrument will react to this part of the atmosphere. You change the water vapor by this much, it's going to have this impact on your top of atmosphere reading. So you get a huge number of these, and it's great. There are two major drawbacks. One, there is a loss of accuracy. It just can't be as accurate as you would hope it would be for those line-by-line models. And two, you can't do these free-flowing simulations where you see the entire spectra at these very small intervals. It does it per channel on an instrument. So it's less useful for developing an R&D of designing an instrument. But it is a lot faster, and something like this can be deployed for what we're looking at in actual retrieval algorithms. So I thought about just leaving it on here and saying all of this is now Agnieszka's problem, which is how do we do this? And I thought that's probably a bit mean, so I'll start doing a bit more on this, but I'll leave some room for her to go into detail. So in general, there are two types of ways you do your atmospheric correction. Either on the go, and that would involve running something like RT-TOF actually on your retrievals. So you're going to do radiative transfer simulations for all of your observations, and try and do the correction. Or you'll take your coefficient model and you coefficient more. So that's the other one. So you get your model that's using coefficients to simulate the sensor, and then you make broader coefficients that break it down into categories you might have readily available: biome, total column water vapor, latitude, those kind of things. And then you end up with a fancy lookup table, which says, for these bands in this area, in this water vapor at this time of year, we're going to correct by this much based on the temperature the satellite sees. So that's about as far as I'm going to go into the actual methods here. Those are the two that go through. But then we can have a look at what we can do with that, because this especially is not going to be perfect. The more we've gone down the coefficient rabbit hole here, we're moving further and further away from the physics, and it's going to miss some of the details. So this is an example from a study that we did here at Leicester as part of LSTM science studies, which was, let's throw a bunch of retrieval algorithms at the same database and see what they do. This is one very small section of that, and that is looking at total column water vapor. And all these algorithms operated in different ways. They all tried to parameterize it differently. So we've got some coefficient-based ones, which is UOL, GSW, and hybrid. But we've also got some ones that do a more on-the-go scheme, such as the OE or direct test and test sort of. And what we find is that even though some of the methods do a lot better, they are all heavily impacted by the total column water vapor here. It has a big impact. So that gives us the idea of sensitivity. So when we get issues with our algorithms, it gives us a tool to diagnose how much of this could be coming from something like total column water vapor. But this is more an interpretation and diagnostic tool. When you're actually giving it to users, you'll probably end up lumping it into uncertainty. So this is just an idea of a breakdown. This is from one of the split window retrievals, the URL one. So Agnieszka will tell you a bit more about this later. But you could get components. A lot of people are used to dealing with uncertainty as one number. This is your MST, plus or minus. But a lot of methods, particularly that come out of projects such as CCI, they will give you an uncertainty budget. So they will say, well, these are all the different components that have come together to give you this. And you can separate out the atmospheric components. And this gives you an idea of how much uncertainty is wrapped up in your retrieval based on your parameterization of the atmosphere and your knowledge of the input atmosphere. And they try to combine both these things to give you an idea of what we're looking at and how much that's going to affect your retrieval. And for a lot of users, this is what's going to actually happen. So you're going to deal with this. The sensitivity and the biases are sort of what you're given by the product. And the best way to account for a lot of what's going on with the atmosphere, as well as other terms that are going in there, is to understand the uncertainty that the product's provided with. And it gives you, with the sensitivity, an idea of how you could diagnose this. If there's higher water vapor in an area, you should be able to see the impact that has on the uncertainty and know what kind of range of impact based on your retrieval algorithm that could have on the result you're looking at. So a little bit of a closing summary on this one. So we've got the atmosphere as a key one in the thermal infrared, and it does heavily impact what channels we go for in the first place. But I wanted to also emphasize that it's not just what we choose to go for, but even once we've made our selection, even with nice, accurate sensor descriptions, that wiggle room of you shift your channel slightly still has an impact. It's still going to be affecting your retrieval. You have to account for it in the uncertainty. So we've got the windows, and they are better, but they are still heavily influenced by the gases that are in there. And all methodologies have to deal with this. Even methodologies that don't tell you they're doing this have to do it. There are certain thermal infrared retrieval algorithms, Agnieszka will tell you later, that pre-correct the atmosphere before they start their thermal infrared retrieval. So that means that whenever you see their accuracy of this, they have locked themselves into an atmosphere. So always check, because every algorithm does this. And if they don't explicitly tell you how they've done their radiative transfer atmospheric correction, that means they're relying on someone else to have done it for you, and you need to know what their uncertainties are as well. So a key tool in this, radiative transfer modeling. And there is the slow but slightly more accurate way, and then there's the realistic, and I can actually run my data with it way. And it's important to know how those work and to choose basically what you're doing. If you're doing R&D, if you're designing a novel instrument, it's worth putting the time into a line by line, pulling out all the details. If you've got an existing product you're trying to run it through, you probably want to go more down the RT-TOL coefficient-based route. So hopefully that's given you some idea of what's going on with the atmosphere. And if there's any questions, I'd be more than happy to answer.
Yeah, thank you very much for the nice talk. I was asking about the uncertainty slide you have showed. So there are several different uncertainties.
Yes.
And my question would be how to deal with it. So do they simply add up? So at the end, you're landing with a huge uncertainty of 10 Kelvin, or are they correlated in a way that you, so how do you deal with these multi-uncertainties?
The answer is complicated. In general, there are correlated and uncorrelated uncertainties, and the way in which you combine them changes based on what you're dealing with. A lot of the terms you actually add together in quadrature at the end, which means that it's not quite as scary as it looks if you take all the bigger numbers and put them together. They don't balloon if you were to add them normally. But what you basically have to do is assign the how, if it's correlated, how much it's correlated. And it's not strictly easy to do this for all products at all times. So, for instance, over time, you can have different temporal correlations. You've also got spatial correlation length scales. The answer is it's difficult. Fortunately, and a lot of the work we've done in CCI, which is really looking to put those budgets together, and Darren has done a lot of work on this, but also Claire from Reading has done a huge amount of work on this, and Karen. There's a lecture on Wednesday, which will fix all of the things I'm talking about. But the answer is it's complicated, but it is possible. But I would always say it's better to have a scary, large uncertainty number that represents the truth than giving you a low, nice number that makes you feel all warm and fuzzy, but your numbers could deviate wildly outside of that. I would rather know than not know how wrong I could be.
I'm Ian Pye from Super Sharp Space Systems. I'm going to be talking about telescopes at the end of today. Thanks, that was a really interesting talk. Am I missing something? Why don't people calibrate the atmosphere by looking at things on the ground where we actually know what they are, rather than simply using the information from the different channels to figure out what the atmosphere did?
So there's a couple of things. One, ground calibration is incredibly difficult, especially a lot of this has been designed at the 1 kilometer pixel level. So emissivity is a nightmare. So getting you'd have to be like 25 by 25 kilometers of perfect known emissivity sheeting just to begin with, to have a good source. And then the atmosphere is highly dynamic. So you could do that for your site. You could set up a thing just outside Leicester, 10 by 10 kilometer sheets where you perfectly control the temperature and emissivity. And probably that will hold for a good region around Leicester. Then you cross the channel and you go into Spain, and your assumptions about the atmosphere no longer hold. So you could do it with a very, very large amount of ground stations in just about every conceivable place. But even then, you'd have an uncertainty. The further you move away, it just gets less accurate. So it's the probably practical limitations that I think, even if you could come up with a theoretical model and framework in which it works, you basically have to pave the earth in known targets.
So if you have more resolution, maybe that becomes a more viable solution, is that
if you've got more resolution, the ground part becomes more viable, but you're still going to have I move a kilometre, 2 kilometres down the road, what's happened to my atmosphere? The dynamics can change so much that the relationship you build over that point may not be valid 2 kilometres away. And that's without elevation and stuff, which could also throw a spanner in the works.
Thank you for the presentation. So at some point you mentioned the use of lookup table to speed up the retrievers.
Yeah.
And you said that one dimension could be the water vapor total column.
Yeah.
I had in mind that in the thermal infrared, also the vertical distribution could also impact the result. So the question is, based on your experience, is it enough to use total column for this parameterization, or would this lead to larger errors?
Is it enough? No. Are there limits where you have to draw your lines for your lookup table? Is the practical answer. Again, if we could, we would use the full line by line for all of them and get a perfect idea of what's going on. What we're looking at the lookup table is putting things into bins of what we think the dominant factors are that we can get the best retrieval we can within the scope that we have. So vertical resolution absolutely does play a role in it. A lot of the coefficients are therefore key to biome and they're key to latitude, and you have climatologies that you try to bin by. It's a proxy, but it's the best we can do in a lot of circumstances. That doesn't just mean you have an infinitely large lookup table. So the answer is yes, in theory, but in practicality, we have to draw lines somewhere, and vertical resolution isn't included in any that I'm aware of.
Thanks.
I have a question, sorry. How are these validated on the ground then? I mean, for optical sensors, you have, the radiometric calibration network, known sites, known characteristics, and, you fly over, validate data products. If you cannot put a 10 by 10 kilometer seat above a city, how do you validate?
So I'll first plug an advert. There's going to be a session later on in the week. Is that right, from Jazz? Jazz is there, and he will give a good idea of the validation later. So he'll go into a lot more detail of this. In general, I'd just say, by the way, this is thermal infrared, not specifically land. So you can actually do a lot of validation over the oceans because there is a vast buoy network that gives very good coverage, and you get incredible amounts of data that you can then validate over the ocean with. So it's a completely different kettle of fish over the ocean. The ocean, you've got tons of this buoy data, and they've got huge validation activities. Over the land, I'll let Jazz get into the details when it's his talk about what's going on there. You are right, we don't have these sites, so we do the best we can. We choose as well as we can homogeneous, as well as we can well-characterized sites. But it is important to note that in any of these, people sometimes make the mistake of saying validation equals truth, and that could not be more wrong. The validation has its own bias from the truth, and it has its own uncertainty from the truth. So it's an intercomparison between the ground and the satellite, not a strict validation of this is correct, and the satellite is trying to match it. But you're absolutely right, there is a huge issue there. But Jazz will tell you how he's fixed the whole thing.
Thank you. I'm not familiar with atmospheric correction, so I guess my question is if you can elaborate a little bit on the mathematical formulation of the line-by-line model. Is that just the class of problem? Is this a boundary value problem, like differential equations? Because I'm wondering, can GPUs, the newer GPUs, could be used to actually accelerate all this? Because this is one of the things they can do really well if it's a boundary value differential equation model.
It varies from model to model exactly how they're dealing with it. In general, I would say you definitely can speed things up by splitting it into chunks across multiple different systems. I imagine GPUs are well placed to do it. I don't know if that would be enough because, for instance, if I could give an example, so RFM for a particularly complex problem we look at, RFM was looking at just under a minute for a calculation. RT12 was 200ths of a millisecond. So that's the order of difference that we're looking at here. It might well be able to cover. I don't know enough about GPU. If it can, that's fantastic. I know that a number of people have been trying to speed up those kind of models and haven't been able to match those coefficient-based ones. So I'm afraid it's slightly out of my expertise, but it hasn't been done yet. But people are definitely trying to speed up these ready-to transfer models.
Sorry, maybe a very naive question. At the very beginning, you showed the spectra with some bands.
Yes.
And you pointed out that the band containing multiple different features, especially from ozone, is one of your biggest contributions to uncertainties, or just sort of for the temperature determination. My question is, are you already in a sweet spot for the actual band definition in terms of size? I mean, if you shrink the bands and put more bands, you lose signal to noise, but could you?
That is a big problem, which is I would love to shrink the bands and pack it full of a dozen bands, but the NEDT, which is what we refer to as the thermal for the signal to noise, is important, and it becomes very difficult to get a acceptable NEDT when you start doing this. There's somebody sitting behind you who knows this all too well, Dave. But yeah, we would love to. And if you could offer me the same NEDT or approximately I've currently got and put a dozen bands in there, I would definitely do it. But we can't. There's a limitation. I don't know if we would physically, because it's just photon counts, the amount of noise we're getting there. If you narrow your band, the amount you're able to capture is just so small. Yeah. It becomes to the point where it's just easier to start accounting for features like this than to deal with the extra noise.
Hi, thank you for the talk. You mentioned about the atmosphere having an impact on the choice of channels you use. Does that mean at different locations, for example, tropics versus, I don't know, like temperate climate?
Yeah, so I more meant that in when they're designing instruments.
Okay.
It heavily affects where they place the channels. It could have impacts if there are high level variability. So if you're in a region that has very high ozone contributions, you may have a larger uncertainty on this channel here. So you may have to increase the uncertainty on that through your retrieval. I don't know that it would ever, because they try to avoid it, be at the point where you would drop the channel. I think they deliberately placed them to the point that that wouldn't necessarily be viable. But you could have increased uncertainty. But I definitely meant it with channel selection. So all three missions I mentioned earlier, SVG, LSTM, and Trishna, have had huge science studies making sure they're placing their bands as best as they are able to maximize the information we get, but also to avoid atmospheric contamination like this.
Okay, thank you.
Are there any more questions? Yes.
So just to comment on the previous question on can you reduce the bandwidth and get more data? The answer from a practical spacecraft point of view is yes, but then you're limited. So you could do forward motion compensation and effectively slow the ground down and integrate for longer, and then you can increase in visible optics. You can increase your SNR. In midwave thermal infrared, you can increase your NED. But of course, that means you need to predetermine a point of interest on the ground, and then you need to tell the spacecraft, I want to take a photo of that. And of course, then you're, rather than just hoovering up data on a one-by-one basis, you then have kind of dead zones where you can't image, two targets right next to each other.
And it's important to note that even with that, there's a trade-off. So while you would be bringing down your uncertainty by reducing the NE delta T, you're also going to be altering your observation geometry, which means that when you're looking at things, another uncertainty. So if you're looking at a flat field, you probably don't increase it too much, a nice homogeneous plane. If you do that over the urban environment, you could be looking at a completely different facet of a building, which is a sunny, shady climate. So it's a great idea to reduce the NEDT, but yet careful deploying of it, because otherwise a different uncertainty could spike. But these are exactly the kind of trade-offs we're looking at in not global operational missions, but in smaller missions that have specific objectives, absolutely longer integration times could be something for a tasked pointing instrument.